then we have hydraulic modification method. So what happens is, this is mainly applicable for soft clays. In case of soft clays, the main issue what we suspect is consolidation settlements. So once our foundation is resting on the soft clay, in a long term we will have a 300 to 400 mm settlement. So that is not acceptable. So in such a case, how do we build the structure? It may be taken using a pile foundation, or then since we have to see how it can be made as a cost-effective option, this is one among that. So this is a hydraulic modification, where whatever we are seeing here is called as the prefabricated vertical drains. So this will be like a vertical drain. So there is some improved drainage path created. So the free pour water can move to this drains, and as well as there is horizontal drains given here. So it helps in the easy flow of the free pour water. So once this water is moving, there is increased rate of consolidation. So total settlement, we are expecting it to happen in some 7 or 8 years, depending upon the type of soil and depending upon the consolidation parameters. So by this, we are improving the rate of consolidation, and the full consolidation can happen in 6 to 8 months. And then we have to perform the investigation and find out what is the improved parameters of the soil. After that, we can do the design. And this is a preloading which will accelerate the consolidation. After that, we have modifications by inclusions and confinement. Like this is a method which we see in reinforced walls. Like there will be some strips placed above which the filling will be done. So the strips is going to give sufficient friction to take up the force. So this is for reinforced walls. Then geogrids, it's mainly used for like face protection walls and all. Then for beneath pavements, we can give geotextile for the proper dispersion of the loads and improving the bearing capacity. And in this method of inclusions itself, we have Vibro compaction method. So here we are including some foreign material and improving the existing soil. So here what we see is, this is called as a Vibro float. So here we will be just vibrating and moving down, and then so we can see what is the hole diameter in the initial stage. And then there will be input of the stone material. There will be vibrations by the Vibro float, which makes the stones to bulge out. So because of this bulging, the sand or the soil in the side gets densified. And once it's coming up, we see the final stone columns to be prepared with a higher diameter. So initial diameter, usually stone columns can have a diameters of 600 mm to 900 mm. That's the most commonly used diameters. And this will be arranged across the site in a triangular or square pattern. Usually triangular pattern gives a better bearing capacity satisfaction. So this helps in increasing the shear strength of the soil, stiffness, and it reduces the liquefaction potential. So we have seen few of the common modification methods that we may be using. So now we will move on. What are some common problems? So as I told, we may have to face soft clays. So wherein we can use pile foundations and take it to deeper depth, or we can go for this prefabricated vertical drains and hydraulic modification, provided the client is giving us time for that. Suppose the project duration is only 2 years and the structure construction itself is going to take that much time, then we don't have this time for waiting for the hydraulic modification. So in such a condition, we have to directly go for the piles. And in soft clays, we have to take a factor called as negative skin friction, because it will go on consolidating once the load is coming. So those things will be more in detail. So then we will see loose sands. So loose sands also has to be improved by any modification, maybe some replacement with rubble soiling. Like loose sand, we can replace with some boulders, and that will help in higher dispersion of the load and reduce the pressure coming on the loose sands. Or it can be modified using the stone columns, which will densify the soil. Then there are cases where we have seen filled up soils, expansive soils. Expansive soils will swell when it comes in contact with water and shrink during dry seasons. So because of this swell and shrink, the heat or whatever is caused, that is going to lift up the structures. So if our structure, what is coming there is a huge structure with high loads, then there is no effect, or we have to check what is the swell pressure coming up. And if the downward load is more than that, then it's not going to be a matter. But suppose we have small chambers like pipelines coming across or small ducts, the pressure is less. Suppose the pressure is 12 tons per square meters. Uplift or this swell pressure is 14 tons per square meters from the lab test. Then it's like we have to give some replacement layer. Either we have to replace that full layer of swelling portion, or we can go for a cohesive non-swelling layer, which is usually taken based upon Indian standard 9451, which is for canal linings. Then we have liquefiable soils, which we see in further slide, and there can be presence of organic clay or decomposed material. So this is some cases which I have encountered. So this is filled up soil. Here you can see plastic dumped waste materials or this bags, clothes and all. So we cannot keep our foundation in such a condition. We have to excavate, remove it and go for a deeper depth. So that is what option we had encountered here, because depth of this fill was some 1.5 meters. And in this case, here we can see there is a black strata which is seen here. That is organic clay. So it may be long back some vegetation or something, and later the soil might have got deposited on it. So this decayed. So this is a soft soil of like in value of 0 to 2 coming at some deep depths. So whatever photo I'm showing here is a depth of 10 meters. We had a foundation coming at this 10 meters and we cannot go any further. So what we did is this organic clay was improved by a chemical modification method by cement slurry, which was used, and the method is called as a deep cement mixing. If you have to know further, you can just search that method, deep cement mixing. So it is used for modifying deeper depths, soft strata. We will not modify the soil in the top, we will modify the soil in the bottom or at a deeper depth. Now we will see just brief about liquefaction. So this problem I have usually encountered for projects in Delhi, where the seismicity is more, or for projects in near to Bihar, then Chandigarh. So what issue we have, whatever the image we are seeing here is from a famous Niigata earthquake in 1964. Here we can see the structure as a whole has failed. There is no problem to the structure, but failure was geotechnical. So this is to liquefaction. So what happened is during the tremor, the excess pore water is trying to escape out. So when it tries to come up, the effective stress of the soil gets decreased, and it decreases and becomes zero, and it behaves like a liquid. So there is no possibility of the soil to take the load, and the structure has failed. So in such a condition, how we can improve? It's like we have to improve the density of the soil by using maybe stone columns or driven piles, or by using some dynamic compaction. So we have to improve the density of the soil, and it's always better to provide some drainage layers. So if in case of stone columns, we are including some drainage layers, so easily the pore water get dissipated without affecting the soil in between. Now we will move on to a case study. So it's like a just brief case study. So here this is the a part of the soil report. Here we have the SPT values as well as the lab test results reported. So at 1.5 there is N value of 4. At 4.5 it's 5, 7.5 18, then 33. So here we have soft soil changing to medium stiff, changing to stiff, and very stiff, hard. So here we can see the grain size analysis results. So gravel is 0%. In this disturbed sample, they have collected and performed this grain size. Sand is 2%. Silt and clay, silt is 76 and clay is 22 by the hydrometer test. Also, Atterberg limits are showing like liquid limit of 35, plastic limit of 18, plasticity index of 20. This is termed as CI soil, which is clay of intermediate compressibility. And here the SPT is performed. Then undisturbed sample is collected at 3 meters depth. In undisturbed sample, they have provided what is the field density what is the natural water content, and undrained unconsolidated shear test was performed, triaxial test is performed, C and phi values are reported. Also, consolidation test has been performed in this layer and CC values reported. So here we can see it's CI layer changing to ML. ML is silt of low plasticity. So here at-above limits are not there, so it's non-plastic. So clays and silts, it's like fine-grained soils. Clays will also always have a plastic behavior. It gives the cohesion. In case of silts, it can have a plastic or non-plastic behavior. If it's a plastic behavior with at-above limits reported, then it will have a cohesion value. But if it is a non-plastic silt, then the silt behavior is like friction only. So that's why here whatever we are reporting is friction value. So here what we have to interpret, as I told before, we have to check whether this shear parameters are matching with the SPTN values or not. So here what I'm seeing is C value of 0.55 kg per centimeter squared for an N value of 4. So I've checked with this correlations. So based upon that, I was getting only 0.26 as the C value instead of this 0.55. So I didn't rely upon these values. I used that values for my further design. So here, just for your understanding, I'm just putting this plasticity chart. So here we can see this line is called as the A line. This line represents plasticity index of 0.73 into WL, liquid limit minus 20. So liquid limit 35 line is this one. This is liquid limit and here is the plasticity index. For liquid limit less than 35, it is called as low plastic. Between 35 to 50, it's called as intermediate. And greater than 35 is called as high compressible layers. So here, above the A line, it will be the clay properties and below the A line will be the silt. So it's along with the size of the particles, we have to see behavior of the particles also to identify whether it is a clay or silt. The silt size may be more, but behavior is clay means it may be reported as a CI or CH soil. So just for your understanding. Whatever case I am showing here, this project is a sewage treatment plant, and here my structural team has given me the SBC, safe bearing capacity requirement of 12 tons per square meters or 120 kilonewton per meter square, and the foundations proposed here is rectangular strip and raft foundations. So here I am having at some 0.5 or 1 meters depth, I am having 12 tons per square meters coming into this. So I have to check whether the soil is sufficient enough to bear that pressure or not. So based upon this C value, whatever I have told, cohesion value, whatever I have told, I have used Tersagi's bearing capacity equation, CNC, SCDC, IC, and I have found out how much is the bearing capacity. So I was getting only somewhere around 5 to 6 tons per square meters. The pressure from the structure is 12. So we have to see another option. So it is either ground improvement or pile foundations. So before telling about here, if it's clay soil with very soft nature, like N value of 2 or 0, like marine clays and all, then in that case, we may not be able to go for this ground improvement, what I am telling. So it's N value of 4 above soft clays, then we can use this method. So here we have seen for ground improvement and pile. So ground improvement with Vibro stone columns was seen, and it was found to be more cost effective. So here whatever we are seeing is this foundation outer, and here we can see this other stone columns which is proposed. The stone columns, you can see the arrangement is a triangular pattern. So this triangular pattern was found to give more effectiveness in giving the bearing capacity. So here we can see another important thing is there is some additional rows given beyond the foundation outer. This additional rows is very important to give the confinement for the stone columns. To get this SBC here, we need to have this extra row here. So this is how the stone column was designed. It is based upon Indian Standard 15284 Part 1. So this gives clear description of how the SBC has to be worked out for in the case of sand or in the case of clays. So here it was clay, so I have used the clay equations. It's very clear, you can also do the calculations. So what we have to do is, before doing the improvement, what is the SBC? So whatever I have seen, 5 or 6 tons per square meter, that we have to estimate. Then using this diameters, first we have to assume some diameter. I have taken 800 and 900 diameters. So 800 diameter. So usual stone column spacing is 2 times of the diameter varying to 3 times of the diameter. It should not be closer than 2D. If it's closer than 2 times of the diameter, then we may not get the required capacity per stone column. Also, it will be then turning out to be very costly, because once this is densified, then making a hole in this densified soil will be very difficult. So 2D to 3D is the usual spacing. So for first check, we can take maybe 800 dia at 3D spacing. So it's like a trial and error method. So with that spacing, we have to check what is the area replacement ratio, and then how it's going to improve the SPC. It's mainly based upon the capacity in bulging. It's how this stones are bulging and what is the improvement because of that. Then surcharge effect. After the stone columns is built up, we will have a granular layer, which is called as a granular blanket of a minimum of 0.5 meters placed on the top of this. So that will help in easy dissipation of the pore pressures. So that is giving some surcharge effect, and then how this bearing capacity of intervening soil comes up. So all this summed up together, which gives us the total bearing capacity. So I found that for this location, 5 to 6 tons per square meters was the previous one. After improvement, we got 12 tons per square meters. So how do we check? Here we have installed the stone columns, or we are going to install the stone columns. How do we check? It's by the field testing. So we have to perform first an initial testing, then we have to go for first by initial testing, we have to ascertain that it is possible. By initial testing, I mean we have to do some boreholes, do some stone columns away from our structure. So it's like it can be a single or a group column load test. Here what I'm showing is a single column load test. This plate load, whatever is putting, is on just a single column. These columns are for the confinement. So for initial load test, minimum of 6 stone columns we have to have. And then on this, the loading will be done. So if this is acceptable, then we will go for the installation of the stone columns for the main plant. So here, this is termed as acceptable if the settlement is in the range of 10 to 12 mm for a single column load test. For a group column load test, there will be more layers of stone columns to confine it, and this plate load will be given on the 3 stone columns together. It means like when it's arranged in a triangular pattern, 3 of that corners of the triangle will be the columns over which the plate load will be done. So that will be acceptable if 20 to 25 to 30 mm is the maximum settlement coming up. So now we have seen one case study wherein there was a poor soil. It was an option of pile or stone columns. We have selected stone columns as it was found out to be the most economical one. So we'll see the conclusions. So as per our discussion, we have now understood what is the relevance of the soil investigation to understand the type of soil, because it varies. And I can say, like, for one of our projects, we were having a borehole taken which was showing sand till some 6 meters depth followed by rock. So the next borehole taken was showing 8 meters of depth of soil followed by rock. So our design in the initial tendering stage was done based upon that. Later, when we got the project, we did more numbers of boreholes. At that time, we were finding boreholes showing similarly 8 meters depth of soil followed by rock, but there are boreholes which are showing 13 meters depth of soil, then rock. So in the same plot, I got rock at very different levels, because of which there was a huge difference. So this shows how important is the soil investigation for each plot. It's like we have to get more numbers depending upon the importance of the structure or the impact it may have. So, so we have discussed all the common problems which we have faced, like soft clays, loose sands, liquefiable soils, or such conditions. And then after getting the soil report, depending upon the type of soil, we have to select what is the type of foundation to be taken, which should be cost effective also. So geotechnical engineers, we can have a career like, mostly after BTech, we have to go for MTech and pursue masters in geotechnical. Then it can be campus placements majorly. So we can have placed in highway sections wherein we will have over bridges or some big tolls and all. So such cases we will have the requirement of geotech engineers. Then in metros, we will have deep excavations. Then tunnels may be there. So all are very interesting geotechnical sections. Then even whatever section I'm working in, water treatment section. So what is the issue with water treatment section is we are getting wastelands or very near to the river beds. So we are having very criticality in the geotechnical conditions. So we have more things to learn. So such conditions are available. And then, yeah, you may be able to go for that. Then main sort of works what we do here, as I told you, like we have soil report review, foundation selection and recommendation. This is the basic work of all geotech engineers, in whether it may be a contracting firm or it may be a consulting firm or you work with a geotech agency. This is the basic work. Then depending upon the type of work, like in metros or water, we have deep excavation involved. So we have to retain the excavations. For that we have support systems which is to be modeled. So that those are some bigger works which we do here. And then tunneling, all such works comes up. So if you have a real interest in geotech engineering, it will be a really interesting one. So I would like to conclude my webinar here.